So today I'm going to review a little bit about what we've been talking about with respect to the censors, the referees, and mediators. Basically, those three groups are have turned out to be a very useful and ultimately flexible way of modeling detections. As one of the things that comes up when we first start talking about discrete event movement is, what happens in between when you start move and you end move. What can go on. Because again, going back to first principles of discrete event simulation, nothing happens in between events that are scheduled. So the implication of that is that if I have a unit a mover that starts move, and if nothing happens when it reaches its destination, if nothing happens in between that, then the simulation simply advances time to that ending time, the time when it arrives at the destination, and continues on with whatever events are there. If there are intervening events, then it deals with that as well. And these are some of the potential intervening events that could occur. And for our purposes here in this introductory class for this, we're going to basically stop with the detection piece of it. And as you may guess by now by the names, what I've been presenting is the simplest version of all of these. And as you've hopefully seen, when you move from simplest to simpler, as I've asked you to do with the movement, then it introduces a richer set of possibilities. The most significant one of which is the fact that the things like the start move or the end move event has as its argument in the simpler version a reference to the mover that was actually performing that event. That becomes important when dealing with things like the sensing. And in the simplest version that we're talking about here, we'll see that there are limitations to this simplest approach. That's not cause for concern, especially if you consider the bigger picture of the iterative modeling approach that I keep babbling about, namely that a useful way to implement any kind of feature in your simulation model, or any other model for that matter, is to start with the simplest version that does something. So with the mover, we had the simplest way of kind of getting from one point to the next. And continuing with that thread, we are looking at the simplest approach using discrete event language to modeling this detection problem or sensing problem. And what we've come up with are these, again, these kind of three groups of classes, one of which are the sensors, a corresponding one are the mediators, and then this referee is also an important element to that. And then when we get to the end, we'll see that it falls short. In fact, in trying to implement just slightly more complicated scenarios, we'll start to see that there's a limitation of this approach, which in turn suggests an improvement, and that improvement is to be determined. Anyway, so the the idea of the sensors is that they're actually more passive than we might imagine. It turns out that it's a useful design to have an abstract superclass and then have concrete subclasses. The idea of the abstract superclass is that that does everything that every sensor is going to do. And the main thing that it does is it maintains a list of contacts, that is targets which have been detected, and responds to detection and undetection events. So when there's a detection event, the argument to the detection is the thing that was detected, and the undetection event is the thing that kind of was undetected, and so it's removed from the list of contacts. Every sensor in this scenario, in this approach, in this framework, is going to have that functionality. What it doesn't have is it doesn't have additional parameters that define how the time from when the target enters the range until it's detected is done. In other words, in our little canonical representation, when the target is coming through here, we have the enter range, the enter happening as soon as it steps over the footprint, and then sometime later, there's going to be a detection. And it's that time in between that we're interested in. So where do we get that? So the idea is that a cookie cutter has, for a cookie cutter, that time to detection is equal to 0. For the constant time, the time to detection is just some number which could be greater than or equal to 0. And then today I want to talk about a third one, which is the constant rate. And for that, the time to detection is going to be an exponential distribution. In other words, now with this third one, it's going to, and what we have here is the mean time to detect there. So this third one starts to get a little bit more realistic, in the sense that when you look at actual sensors, for a variety of reasons, either noise in the environment or differences in how the signals are spread and everything, that the time to detect a target, say this, even the same target by the same sensor, is not going to be exactly the same at each and every time. So that's when you move to modeling the randomness in there, that we're starting to get a little bit more realistic in that respect. The corresponding logic, though, for each of these things is implemented in the mediators. In other words, the simplest cookie cutter mediator listens to the referee for the enter range event and then schedules the detection on its cookie cutter sensor immediately. The constant time mediator, they all listen for the enter range event. And remember, the enter range event has as its arguments the target and the sensor. So the constant time sensor does kind of the same thing, except that it delays the detection by this fixed amount. And where does it get that from? That's the parameter in the constant time sensor. So the implication of that, as a consequence, the same constant time mediator can serve all of the constant time sensors, regardless of what their time to detect parameter is, because the logic is exactly the same. As long as it's a constant time sensor, it will read the time to detection from the sensor, and it will get the sensor as an argument to the enter range event. Now with the constant rate sensor now introduces an additional issue here. So there's a, let's call it the mean time to detect. And so we want an exponential distribution with a mean given by the mean time to detect, which is a parameter in the constant rate sensor. So how can we do that in actually a fairly straightforward way? And as we will see, the way, a way to do it is to have a parameter that's an exponential with a mean of 1, and then simply multiply it by the mean time to detect, which it gets from the sensor. Okay, so and if you sort of think back to your, hopefully you're in your probability class, they talked a little bit about the exponential distribution. It's a very important distribution. Maybe not as important as the normal distribution, but it's an important one nevertheless. We've been using the exponential distribution almost since day one as the time between our arrival events as one of the possibilities. But it turns out that this is something which can easily be done. Okay, well, we'll see how that works. And again, as the referee, now, because in our simplest version of this, the things like the start move and end move events did not have a reference to who was doing it. Because again, we started with the simplest possible case, and in the simplest possible case, there was no need for that. And so one of the consequences is that the simplest referee needs to have to know who is it adjudicating between. So really the only way to do that would be for each instance of the simplest referee to create multiple instances for each sensor target pair. And as we'll see in an example, you could have 2 different referees for different sensors and the same target. And correspondingly, you could have the same sensor, but multiple targets, and you would need a different instance of the referee for each one of those. And as we'll say, and if you think about it, that's, as we critique this, we'll see that that's not the ideal thing. But anyway, just to review a little bit about what this abstract sensor business is. So it has 2 parameters. One is going to be a simplest mover, which is going to be used for location and velocity, and the maximum range. So the maximum range is that what we've been calling R. So that's the size of the footprint. And again, since we're doing the simplest possible one, as we go through this, we will deal exclusively with circular footprints. As you're no doubt aware, there are situations where we have, where like a sensor may have like a cardioid shape, or you might even have situations where you have a shape that looks like this, where it's kind of pointing outward. All of these can be handled with just a little bit more of an effort. Just in other words, the referee, so if we had like kind of this cardioid shaped thing, we would need a mathematical representation of this, and we would need some mathematics to be able to compute, say, the time between when we started to move here and we entered there. And it turns out that for reasonable assumptions on what the shape of these curves are, all of that can be done. It's just more complicated. Okay, so if you're thinking, well, I know that here the certain sensors have these different footprints, and so what about that circular one? Again, as part of the iterative development process, if we were in a situation where the footprint of the sensor was a critical thing, then that's something where what we've been developing would be a shortfall. And so if that was a critical element to the, and that particularly comes in with, say, forward-looking sensors like this one. For something like this cardioid, I mean, the difference between that and a circle can sometimes be fairly minimal. So the impact cannot necessarily be that great. For things like the cone-shaped one, then it is quite a bit more significant. That is, the difference between this cone and, say, a circle with the whole thing is rather substantial. So that would be a case where we would have to consider, there we'd have to look at things like, is it going to, like, is a target going to cross here, or is it going to cross here, et cetera. All of that is fairly straightforward and can easily be handled. Okay, but again, we're not dealing with any of that. We are dealing with, it's like I click on this thing and it doesn't respond. Okay, state variable, again, that's set containing the context. And this is kind of a, again, not entirely necessary, but driven by what I've been calling the programmer virtue of laziness. And that's an idea called delegation. You don't have to remember what that word is, but the idea is this, is that we already have these movers that can kind of go from here to here, and we can direct them according to a path mover manager, a patrol mover manager, and a random mover manager. Those are the three that we're dealing with. There are, just by the way, for that, we won't cover it, but there are many other mover managers that we can implement. The list goes on and on. So for example, there are situations where if we're trying to go in pursuit, so let's say if there's something going like this, and we're here and we want to try to intercept that, there is a way to do that. There's a mover manager that will allow us to kind of go and try to intercept this. So like if we're modeling something like a smart missile, or even something like a patrol boat that's trying to intercept a potential bad guy, then that's something that can be done. Again, all of that is just more complexity. The key thing here, though, is that given that we have movers that do that kind of thing, if we were, and because we want to implement the idea that a sensor can be moving around. So say if we want to model, say, a UAV that's kind of going out and looking around for stuff, well, we need to have our sensor moving around. We can't just have it stationary if we want to have a decent model of it. So at some point, the mover needs to be able to move around. Now, what does it mean to be moving around for the most part? The key thing, there are kind of two elements to that. One is that there be some kind of mover manager type of thing directing it. And we already have mover managers that can move the movers around, but the mover manager can't move the sensor around. So how can we make the sensor move around when we only have movers that can move around? Well, the lazy approach, and again, the laziness being a virtue here, is that we give the sensor a parameter that's a mover, and this is the mover that's going to be used for its location and its velocity. Those are the key things that the referee needs in order to calculate the enter range and exit range times in the calculation. In other words, what it needs to know is the relative location of the sensor and the target and the relative velocity. So if it knows the location of the sensor and the velocity of the sensor, in addition to the location and velocity of the target, then it can compute the relative location and the relative velocity as we showed yesterday. Okay, so the idea is that then this mover instance that's a parameter for the sensor is going to give the current location and the current velocity. So say whenever the referee says to the sensor, "Where are you?" the sensor says, "I'm with stupid." And if the sensor says, "How fast are you going?" again, it says, "I'm going as fast as stupid." So this is stupid. Okay, so again, this is the abstract one. And so the idea is that, see, this simplest mover here that the abstract sensor is listening to, that's its parameter. So it's listening for this. And so you see when it has a start move event, then the sensor will hear that. And when our simplest mover has an end move event, the sensor will hear that. And when it hears these, it will schedule the corresponding ones, again, with 0 delay, so that the referee knows when a sensor starts moving or the sensor ends moving. And then here are the detection and undetected events. Again, the argument for that, M is the mover that's the target, not the mover that's listening to for this. Because that's basically, you can think of this as, like if this is a UAV and this is a like a radar on it, then you think of the radar being put on to the UAV. Now, one implication of this, by the way, is that it's a fairly straightforward matter to have more than one sensor on the same mover. In other words, if I have another one that's listening to the same mover, it could be just sort of another sensor. It could be a different type. It could, as this one mover moves around, then both of the sensors are going to be hearing these start and end move events, and then the corresponding referees will be able to hear those and respond accordingly.
Clarification, just a question on clarification.
Sure.
In the simplest abstract sensor, the start sensor move and the end sensor move, those methods will not be written in the simplest abstract sensor. Those are for no, I'm sorry, maybe I reversed that.
Yeah, they're for well, see, here's the thing is this is, thanks for bringing that up. Just as a general point, if you have a component that's scheduling an event, and the event that's being scheduled doesn't have any state transitions and it doesn't schedule anything else, then you can either write that event in or leave it out. You can actually leave it out without any consequences, as it turns out, because so for example, look at the start sensor move does not have any state transition. It doesn't schedule anything else, but it will nevertheless still be heard by the referee. Its only purpose is to be heard by another component like the referee. It never hurts to write that in. To be honest, I'd have to look at my code again to see whether I wrote it in or not. If the only criterion is whether it's confusing or not. So if it's confusing to not have it written in, then it should be written in. And if it's okay, if it's not confusing to not have it written in, then it's okay to not have it written in. Does that address it? I hope.
Yeah, I think so. I think that helps a little bit. I found myself getting tripped up on that a couple times when putting the code together.
Well, when in doubt, it never hurts to actually write it in. In other words, every event in any component should have a do method, and if you do that, that can never hurt.
But when it's there, there's nothing in the method, right?
Correct. I mean, yeah. Yeah, just as in here, like and we'll look at the code in just a little bit, and we'll kind of see how that. Well, or maybe we should maybe we should look in the code right now since we're bringing that up. Let's see if I can find it. Okay, so here's the simplest abstract sensor implementation. And let's find the, okay, so here are the do detection, do undetection. Okay, so here's the do start move and await delay start sensor move. And I see that it is not written in. So, my question is it, would you rather have it written in or not written in? It's, again, it might be just sort of the laziness. Let's have it. Let's write it in. Again, there's nothing in it. But okay, so it's there, and it doesn't hurt anything to be there. It doesn't hurt anything to not be there. Okay, does that sort of clarify things a little bit?
Yeah, it does. Thanks.
Okay. Okay, but I mean, as you can see, though, I mean, we're there's really nothing new in terms of the discrete event stuff, in terms of the event graph stuff going on. I mean, the only slightly new thing is the fact that we're defining an abstract one of these classes that we're going to subclass later. But as we've been doing, we have been subclassing these event graph components for a while. Typically simple ones, and this is a very simple one as well. In other words, the subclasses of the sensor subclasses do not add any events. In other words, these are the only events that our sensor is going to be concerned about. The detection and undetection events, which cause us the main state transition, and then the start, move, and end move events, which are important for the referee to hear so that it can know whether to schedule an enter range or an exit range. All the subclasses do are add parameters for the mediators to be looking at. We'll see how that goes. So again, the simplest cookie cutter sensor is just a simple subclass of that, and it doesn't add any additional parameters. So that's really the simplest one. And the way that works is, let's see, simplest cookie cutter sensor. Come on. We see it just simply extends the abstract simple sensor and overwrites the and writes constructors, because if you don't write the constructors in the subclass, you only get the zero argument constructor by default, and that would kind of work, except that we would not have our parameters here. The constant time one, again, that's another. It adds a single parameter, what we're calling time to detect, and so again, we extend it. The most work we have to do is with the constructors. Okay, now, and here again, just to show the other way, let's see, I think in the constant, in the cookie cutter one, let's see, that's the cookie cutter. What the heck are you? Okay, so there are two approaches to the master and zero argument constructor. This is one where I call the zero argument constructor using this, and then I have to explicitly set my parameters. The other approach is to directly call super with the 2 parameters that it needs, and then just set the additional parameter, and then leave the 0 argument constructor just kind of hanging out there. Both are absolutely correct. It's just that there are competing criteria. One is that, I mean, in general, from a Java perspective, a best practice with multiple constructors is to have one and only one constructor that calls the superclass. And that's what this one does. In other words, the master constructor calls the 0 argument constructor, which in turn calls the superclass constructor with the 0 arguments. But then the only thing left to do is to set the parameters, which this one does. In this approach, but you notice that here I have to write 3. I have to write. I could have left the super out, but that was just to make it explicit. But here I have to write 3 lines of code, and I have to remember to kind of set these. Here, this violates that practice of having only one constructor called a superclass, because now both constructors are calling the superclass. See, the 0 argument constructor, nothing's there. That means that Java is going to put super with no arguments in. And that's going to work because there is a 0 argument constructor in the superclass. Okay, but here now I'm just calling super with the 2 parameters. That in turn is going to call the superclass constructor with passing both of the terms. And then I need to set the additional parameter. So you just have to pick your poison, whichever one you're okay with. I'm okay with, as long as it gets the job done. And what's the job? The job is to make sure that all of the parameters are set. Now, the one additional thing, of course, since the time to detect, it could be 0, in which case it's a cookie cutter sensor. So that's fine. But if the time to detect is negative, then that's a bad value. And so we need to check to see if you've given me a time to detect that's negative, then I'll say no can do. Okay, so that's an important thing to identify. Right, now the final one that we're going to talk about here is this constant rate sensor. And so the idea is that it has a random time between the enter range of detection, but the sensor isn't going to be responsible for that. The mediator is. So we just add a parameter, mean time to detect. And so here's what that looks like. We have a constant rate sensor here. So again, we extend the simplest abstract sensor. We add a single parameter, mean time to detect. And again, the structure is the same as we had with the constant time one. The difference, now, we could have been even lazier and had this and used the simple constant time sensor and just use its time to detect as the value. That would have been fine. But it turns out to be a little bit safer to have a separate class for each of these things, because when the mediators are listening, then the arguments on the mediators are kind of the important thing. Okay, so all right, so now let's review the referee. So it's responsible for scheduling the enter range and the exit range events. And mostly because those start move and end move events are the kind of key that triggers this. The problem that we encounter is that because in our simplest version, we don't know which mover had a start move event. In other words, if I'm listening for movers, let's say if my referee were listening to 2 movers and it hears a start move event, the first question is, which mover was it? So the referee needs to know which mover did the start move. Likewise, the sensor needs to know which one it was. Now, in terms of type now, this is where the abstract sensor kind of comes into play. If I make it a simplest abstract sensor, then that means that I can insert any subclass, any concrete subclass of the simplest abstract sensor into the referee. So in other words, the same class of referee can be used for any of the sensors that I have, any of the sensors that subclass the simplest abstract sensor. So it listens for the start move and end move events from the mover. It listens for the sensor start move and sensor end move events from the sensor. And then it has, just for simplicity, we had an enter and exit times event. And what it did was it computes the solution to that quadratic, so didn't fix the question, equation. Microsoft Clippy at work here. Okay, so, and as we have worked out in the methodology, if it gets 2 positive roots, it schedules an enter range with the smaller of the 2. And if it gets a positive and a negative root, it schedules an exit range. And its event graph looks something like this. So it looks, this is a little bit of spaghetti, but let's kind of try to unpack it a little bit. See, first of all, here it has a simplest abstract sensor it's listening to and a simplest mover. So from the simplest mover, it will hear the end move and start move events. From the sensor, it will hear the start sensor move and end sensor move events as well. And so given that, it will, they all call this enter exit times, and then we'll see why there's this canceling edge. That comes about because we'll have a start move and an end move event, both of which happen at the same time, and they'll both get hurt. So for example, if our mover gets to a waypoint and then immediately is scheduled to go to another waypoint, there will be an end move event followed immediately by a start move event. And because we have scheduled the enter and exit times with a low priority, which is not indicated here, then that actually doesn't occur yet until all of this pans out. And when that happens, see, now here's the thing is that let's just, supposing, like here's a hypothetical situation. So let's say that a mover does a start move here. Let's assume our sensor's stationary. So our mover is being directed, let's say, by a path mover manager. And when here's the start move event, it will schedule an enter range event here. But let's say that its first waypoint is right here. And at that point, it will make a slight veer. So what that means is that, let me change the color. So in other words, when that happens, that will schedule an enter range event at this time, at this location, and at a different time. But here's the thing, this old enter range event is still on the event list. And so what's happened is that when the mover made this turn, it needed to schedule a new enter range event, but the old one was still on the event list. So we need to remove that. And how do we remove that? With this canceling edge right here. So if that's the situation. Now, if it's, here's another case. So now, supposing it's the case that when it goes here, instead of just veering, let's say it makes a complete right turn. Now it's never, there's going to be no enter range event at all. So in this case, they're going to be complex routes, and so that's why what you can't. There's no condition on this. In other words, the enter exit times is going to cancel any pending enter range events if they exist, period. And likewise, exit range events. See, the same thing could happen. So let's say we have one here, and then it kind of goes here, and then see, once it hit this enter range here, it would schedule an exit range out here. But then let's say it decides to kind of make a turn here. Now, what'll happen, it will have a negative route and a positive route, and it will need to schedule an exit range at this time. But this old exit range is still on the event list. And so if you don't do anything about that, that's going to happen. So that's why this needs to be canceled. Okay, so you see, I mean, it gets a little bit complicated. But here's the thing, is that if in normal movement, in agent simulations and combat simulations, when you're modeling movement, they're not like bumblebees. They're not changing direction constantly. They're, you know, like if you're an aircraft, for example, I mean, you're not going to be, unless you're in a dogfight or something, you're not going to be continually changing your movement. You're going to be spending a lot of time basically in what amounts to logically a straight shot. Similar, like if you're let's say you're a truck on traveling along a road. Well, you know, you're going to be typically traveling for a fair amount of distance. And so you're not going to be continually jittering around a lot. So these, you know, what can bring this to its knees are just if you are jittering around a lot, then you have a lot of these scheduling and canceling going on. And so that's a corner case where this kind of this approach tends to break down a little bit. But okay, so now the key to all this are the mediators now. The referee is the key to getting these enter and exit range events scheduled. And then the mediator listens to the referee for an enter range and exit range events. And then it will schedule the detection and undetection events on sensors of a given type. And we have a different event graph for each possible one. So here's our simplest referee. I'm not gonna spell all that out, but here's the cookie cutter mediator. So here's an enter range event with an argument of the target and the sensor. So that, again, where does that come from? That comes from here. So this will hear that. And then with the cookie cutter sensor, the delay between the enter range and the exit range and the detection is exactly 0. Now, the one new thing here is the fact that and there's kind of a reason for this, it actually will schedule that on the sensor itself. And likewise with the exit range, as I mentioned, because there's no established methodology for sensors that sort of lose targets, because that's actually a whole different ball game than the methodology of sensors acquiring targets. For our purposes, all of our mediators are going to just lose it with a delay of 0. So when it exits the range, when it hears the exit range from the referee, it says, okay, now you've lost it, and it schedules the undetection event passing the target that it heard from the argument. Now when we move to a constant time, it actually becomes a little bit more complicated. So because now there's a delay between the enter range and the detection event. And you see what can happen is that so here's our enter range event. Supposing the delay is such that it's moving so fast that the time to detect would actually take it outside of the sensor, outside the sensor's range. See, that's one possibility. Another possibility is, of course, that it actually detects sometime later. So that's where we have to kind of look at what's going on. So when it enters the range, basically it says, okay, now I'm going to detect it sometime later. And what's the delay? The delay is the time to detection from the sensor. So say T dot TD, that would be time to detect from the sensor. The tricky part is at the exit range. Now see, at the exit range, see, here's the exit range event. Change color here. Come on. All right, so here's the exit range event. And at that point, you don't know whether or not the target has been detected or not. So if the target has been detected, that is, if this were the case, then we can schedule an undetection immediately. However, if this is the case, in other words, if it hasn't yet detected it, that is, if it's not detected, then what that means is that this detection event is still on the event list, but that's kind of outside the range of the sensor. And so we need to cancel that. Now, that's one approach. We could have taken a different approach and said, well, when the enter range occurs and we look at this time to detect, we could try to figure out whether or not that detection will happen before or after the target exits the sensor's range. Okay, that would be a lot. Basically, it's like straightforward to do, a bit more complex, a bit more computations. We basically have to solve another quadratic equation to kind of get this time here and figure out whether our time to detect is going to be greater than or less than that. What we took here was kind of the simpler one. Okay, so the constant rate mediator is exactly the same, with the exception that now, if T sub m is the mean time to detect, the delay is now an exponential distribution with that mean. And as I mentioned, we can compute that using an exponential of 1 times the mean. And let me show you where that is. We'll have that up, constant. So constant rate. There, oh, there it is. Okay. Okay, so what does that look like? Well, we have a unit exponential random variate. That is, this is going to be an exponential with the parameter of 1. And there are various ways to kind of pick that. As a parameter, it has a setter and a getter, and we have to be a little careful about that. So here, with the 0 argument constructor, I get an exponential with a mean of 1 from the random variate factory. But here's kind of the key thing that, okay, how do I know whether the sensor has detected it? And well, basically I'm saying that if it has not detected it, then I'm going to schedule my detection. And here's where I get the mean time to detect from the sensor, and I multiply it by the unit exponential, which generates an exponential of 1. So that's how you model this exponential time for the enter range, exit range. Now, let's see, do I have time for this? I do not have time for this. Okay, so tomorrow, first thing, I'll kind of just show you what this is. Basically, what the example here is, and I've posted it, or it's in the GitLab of the code. Here's I have a target here, and what it's going to do is it's going to bounce back and forth between, as a control mover manager, between these 2 points. And what I have here are 2 sensors that are going to try to detect that target.